Okay, let's get the clap. All right, let's get to work. Hello and welcome back to Let's Code Physics. I am really excited today to get started a series that has been requested a couple times, and I kind of teased way back in my channel intro video, which I think I desperately need to update. If you're still expecting these videos to be 10 to 15 minutes long, you can watch them in 10 to 15 minute chunks. YouTube will remember it. But this is the problem of studying the pendulum. Pendula, penduli. These neat things offer some really neat ways to study physics behaviors, especially when you start introducing driving forces into them, because you can get these chaotic behaviors that are really interesting. I know we've seen a little bit of chaos earlier in season 1, so I'm excited to get back to it this season. The basic setup is what you see here. You've got a mass, usually depicted as a ball, but it could be a weight or something suspended from a rod. Let's say the rod's got a, well, we'll worry about its length later. We're about late. Yeah. Let's give it a length L. There we go. And so there's, in the very basic model, if this were happening in space and there was no motor on the thing, there's no friction or drag or anything, we'll get to those things later, you'd have two forces acting on this thing, right? You'd have a downward force of gravity, although I suppose that means this thing isn't acting in space. Okay, let's make the traditional, assumptions that you've got minimal air resistance. Maybe you've got it in a vacuum chamber. You're only looking at it for a couple of cycles. You've got the gravitational force pulling down. You've got the tension keeping it attached to the string. Well, usually you think of it as a string. I'm going to be thinking of it as a rod because I want this thing to be able to go inverted and not just collapse in on itself. There's some neat stuff you can do with inverted pendulums. When you look at this, you want to use the rotational version of Newton's second law. So the traditional version is this F equals ma. But in this case, the acceleration is taking place around an axis, so it's actually easier to use the rotational version where the net torque is equal to this thing called moment of inertia times the angular acceleration. It looks a lot like F equals ma, it's just F equals ma for rotation. So this piece here, the torque, is just the distance that each force makes from the axis of rotation. In that case, that's going to be this point right here. Times the amount of force times the sine of the angle between the two. And here's where it gets interesting, is that you've got this length vector going out along the rope here, and you've got the tension pulling in this way. And so you've got a 180 degree difference between those two vectors, and sine of 180 degrees is 0, so the tension gives no torque. Which is kind of nice because it means that this force that we don't really have an equation for, that we can't really solve for, we can solve for it. We can't really experimentally determine very well, except to put a force meter in the middle there. It gives 0 torque, so it totally drops out of the problem. The only thing that gives a torque is the gravitational force right here, which is what you'd expect, right? That's the only sort of external force causing the thing to rotate. So that thing's torque is going to be mg times the length times the sine of the angle there. And that's going to be equal to the thing's moment of inertia. So this is just a point object out a distance from the axis of rotation. So that's just going to be ml squared, mass times the distance from the central point squared, times the angular acceleration. Now the angular acceleration is, so if you think of regular acceleration as being how fast the speed is changing, so it's the second derivative of position, this is how fast that angle is changing. So this is the second derivative of the angle. So when you're doing a time derivative, let me make that dot a little bit bigger. There we go. So when you're doing a time derivative, we usually denote that with dots. You've probably denoted use a prime to denote first or second derivative in your calculus class. That's because you're taking derivative with respect to x. And lo and behold, like in so many other problems, the mass cancels out. So that's kind of nice. So we don't need to worry about the thing's mass right away. And then you can get one of these L's to cancel out, because your ultimate goal is to get the acceleration by itself. So you end up with this acceleration, or angular acceleration, is just the gravitational field divided by the thing's length times sine of theta. So this is all just one number, right? This is constant. I suppose we could change the length of the pendulum. That might be fun to do a little bit later. But that's just going to be multiplying the sine of theta. So this is the thing that's going to be changing. So as theta gets bigger, this theta double dot is going to get smaller because, wait a minute. No, excuse me, that's going to get bigger. The speed is going to get smaller, excuse me. So yeah, so as theta gets bigger, this thing is going to get bigger because initially sine is increasing till we get past 90 degrees. We'll keep it within 90 degrees for right now. So you've got this the acceleration increasing, but it's in the opposite direction. Oh yeah, I needed a negative on here. I had to say no, it's supposed to work against it. It's not supposed to fly away. Yes, there's supposed to be a negative there. Excuse me. The reason for that being that this thing is making it rotate. Let's see, that is the clockwise direction. Yeah, so this thing is making it rotate clockwise. Clocks are negative, so there's a negative there. Yep, there we go. Yeah, torque has 4 pieces. The force, the length, the angle, and the plus or minus at the front. I haven't implemented correctly in the code, so I decided to go ahead and set up the code rather than go through my usual 20 minutes of typos. I did the 20 minutes of typos, just not in front of the camera. So what we've got here is the start of a basic pendulum code. I've gone ahead and given values for the mass and the damping, even though the mass drops out, and we're going to set damping to 0 for right now. We've given the pendulum a length of 1 and a gravitational field of 1, just for ease. Those are basically just determining the units for the problem. And then here I've set up a function to create the differential equation for theta double dot. So right now that function is just this negative g over L sine theta, and lo and behold, that's what we've got down here. Theta double dot equals negative gravitational field divided by length times the sine of theta. Our inputs for this are theta. And I've gone ahead and put in inputs of theta dot, the first derivative of theta, so how fast it's swinging, and the time t, because we'll want to incorporate this a little bit later. And actually, let's call that time, just because there's no penalty on variable name length in Python, so we may as well do that. We can also add in a driving force. I've got this bookmark here for a little bit later, and also let's leave a note here that we need to add driving and damping forces later. Yeah, that's fine. And so we're going to return theta double dot. So basically all it's doing is this pendulum force. Pendulum, no, it's not exactly a force. It's the acceleration right here. So here we've got our initial conditions. I'm not giving a very large amplitude at the beginning. So we're just looking at a theta of 0.2 radians, which is not very many degrees. And we're giving initial speed of 0. So you're raising it up a little bit and then you're releasing it. Then here we've got the visuals created. Actually, let's put in a note that that's what you're doing here. Create visuals. And as always, you want to make sure that you give your visuals a name so that you can modify them later. You only want to not give them a name if you're not going to modify them or destroy them later. Let's see. So we've got here's where all the physics happens. So this is again the Euler-Kromer method. So we increment the first derivative by 1 time step. So we're saying it's equal to the previous value plus the rate times the change in time. That's basically all that means. Same thing for theta. The next value is equal to the previous value plus the rate times the change in time. And then we'll increment time forward. That doesn't really have any impact right now, but it will later when we're evaluating this driving force. And then, of course, we have to update the pendulum bob's position and the axis of the rod so that way we can actually watch it be animated. Okay, and so the pendulum is working, right? This is how you expect a pendulum to behave. That is a little bit, it's bugging my eyes out a little bit with my screen refresh rate. So let's slow that down just a little bit. Actually, let's slow it down. Instead of decreasing the rate, let's actually decrease the dt. Let's decrease it by about 25%. There we go. There we go. That's a little bit better. Okay, so it's going back and forth, just like you would expect. The other stuff that I can change, let's see, if I make this bigger, I should get a larger amplitude, so it should start out higher. Good. You notice it's also reaching a, I think you can tell it's reaching a higher speed there at the bottom. I suppose I could put in a velocity vector. Of course, we're not just interested in watching an animation. We would also like to be able to analyze the results. So let's put in a graph here. So that calls up visual.graph import star. There we go. And we need to set up a G-curve. So we're going to call this, let's call it theta versus time to be a G-curve. Color equals, I don't know why, I always like putting in green for the color. I don't know why. Although does that show up well on y'all's screen when you're watching on YouTube? Let's stick with green for now. And then what we'll do is, all right, I have to remember how to do this. So this is G-curve. Let me remind myself how to use this. I have not set up a G-curve in a little bit. Okay, so it's not referencing G-curve. I should have been able to tell that. You have to reference the thing, theta versus time. So I've been working in C# for black hole battles, and I keep expecting the autofill list to appear, and it's not. I have to type all my variables manually like a caveman. Jeez. Let's see. So we want this to be time and theta. There we go. All right, let's give that a run. Oop. Tuple index is out of range. That's unusual. What did I do wrong? Oops, excuse me. I'm referencing this as an example from before. So position should equal something comma something, right? All right, so I've got my G-curve. I was using a G-curve up here, right? G-curve, ps_graph1. Y'all remember this code, right? All right. Theta versus time dot plot. Position equals time comma theta. What's the problem it's running into? Tuple index. All right, let's actually read the errors. Primitives. Oh, golly. Tuple index out of range. Oh, the problem's in line 29. Oh, right. Because this has to... Right. Sorry, I forgot it's color dot green because you have to access the thing called the list color. Yeah, there's my autocomplete. Hey, how about that? There we go. Okay, so here is the animation and here is the graph. So, all right, we need to set a time limit on this thing, don't we? Or else that's going to get accordion scrunched really quick. So let's do while time is less than t max. And let's say, say Tmax equals, that thing doesn't need to go past 50, I don't think. I suppose another way to do it would be have it count the number, this will be something I'll try later, have it count the number of maxes and mins, and basically have it stop once it's done a certain number of cycles or something. Okay, so what you look at this graph and you say it looks a bit like a cosine curve. And that's a decent approximation to say that this thing is a cosine curve. Because when you look at the original differential equation, when you have very small angles of theta, so when you're only lifting it up by a little bit, sine of theta is approximately equal to theta when you're working in radians. Sorry, degrees, it doesn't work. But when you're, well, I mean, it'll work if you convert your degrees into radians. But when you have really small angles, sine theta is approximately equal to theta. It's called the small angle approximation. It comes out of a Taylor series. It's a really neat approximation. What that means is that theta double dot is equal to a negative constant times theta. And that's the simple harmonic oscillator, right? That's the problem, that's the differential equation that gives you sine and cosine, right? You can think of that as where sine and cosine come from, is from that differential equation. But if you make your amplitude larger. So right now we've got an amplitude of 0.5. And but when you make it too large for the small angle approximation, that sine and cosine behavior is going to go away. So here we've got a much larger amplitude, right? It's coming out here, so almost around 45 degrees or something. You begin, let's see, do you begin to see it looking terribly different from sine and cosine? Let's decrease the T max. Let's just take it out to, let's say, 15. So I want to be able to get in closer there. And let's go ahead and increase this one to, do I want 2 radians? Is that, I think that's going to take it above 90 degrees. Although I need to in order for it to show you that it's not a sine or cosine. Yeah, so here we put in an amplitude of 2 degrees, and this thing is starting to look not like a sine or cosine, right? Because it's like it's a little bit too broadened for a cosine curve. Let's see. Let's make this even bigger. Let's see. It starts out down here, so a value of pi would be all the way up here. So if I put in 3, so this thing is going to almost be pi. Right? It starts out up at the top. Right? This is not what a cosine curve looks like. Right? A cosine curve does not make a U like this. Here's so we're starting it all the way up here. This is not a cosine curve, right? A cosine curve does not look like that. That's like going from an x squared to an x to the 4th or x to the 6th looking thing. So that's why the program is important, because while the small angle approximation is decently useful for small angles, it's not useful for large angles. Of course, the other thing we can test is the period of the pendulum. If you take this thing and treat it like a harmonic oscillator, you get out this result that the period of the pendulum go away. There we go. You get this result that the period of the pendulum should be square root L over G. Oh, and then it's either 2 pi or 1 over 2 pi. I believe it's 2 pi. 2 pi root L over G. That sounds right. Let's double check our reference, shall we? Oops. Let's see. I opened up this just to make sure I had the differential equation correct. Yeah, 2 pi root L over G. There we go. Thank you. I'll cite my source. Thank you. Where are you, title page? Let's see. Come on, this is going to be more effective when I can actually find it. Thank you, Gray Davidson from December 2011 at Reed College for the helpful recap of pendulums. Well, it's not just a recap, it's a thesis, but I read the first part, which was the recap. So we can also test that result by getting our period off of here. So we start out at a maximum. We end at 6.3 something. So we've got 2 pi squared L over G. Our L and our G are both 1. Mass length are both 1, so that's going to give you 1. So it should just be a period of 2 pi. And lo and behold, there it is, right at about 2 pi. Cool. So let's see. If let's say I want to cut the period in half. I would have to cut this thing by a factor of 4 because it's under square root. So if I want the whole thing to get cut in half, I need to cut the L by a factor of 4. So let's decrease the length by a factor of 4. So you notice it's swinging a lot faster now. Actually, I need to change the position of that thing. Let's see. So what I want is let's take care of the display elements down here. Say display position. Do I change its position? What do I do with that? I should have kept my other code out for reference. The gravity simulator. That was this thing. Nope, you just change its x and its y. All right, good. My bad. Let's see. So you just say its x needs to be 400 and its y needs to be 0. So I'm going to try to shift it to the right a bit. Almost. Let's make it 800. There we go. Yeah, so you see it's got a much smaller length now, and so it's oscillating a lot faster. So we decrease that by a factor of 4. The whole thing should decrease by a factor of 2, so it should be right at about pi now. And there we go. So if you want a neat way to measure pi other than using a circle, make a pendulum of length 1 meter. Oh wait, 1 meter? No, excuse me. We need to cancel out the other one. So make a length of about 2. So G is approximately 10, right? So if you make, so actually let's do this. If you were to make, let's put this in real units. So let's make our gravitational field traditional 9.8. If you were to make a pendulum with a length of 1/4 of 9.8 meters, so about 2.5 meters, and you let it swing, the period of that pendulum would be approximately equal to pi seconds. So watch, just by building a pendulum of 2.5 meters. Kind of neat, huh? Let's see if we can break that, though. Let's see what we can do to break that approximation. So let's leave those in there because that's kind of a neat thing to have. So this should be giving us a period of pi, but let's see what happens when we make the original theta larger, because this is another thing that'll break, is this approximation 2 pi root L over G as we get larger angles. Let's see here. So for example, here it's already creeped up to 3.29, so 3.3 almost. So it's already crept away from pi. So we've already broken the approximation a little bit. Let's take this to 1.5. Now you can see it's definitely beyond a small angle at this point. Well, 1.5, you got to remember, is about half of pi, so that's going to be about pi over 2, which is about 90 degrees out here. Yeah, that one's all the way out, already out to 3.6. It occurs to me I would like to have a reference point for where the original position was. So what I'm going to do is oops, that is the wrong code. So what I'm going to do is I'm going to duplicate Bob here. So let's call it Bob 0. Bob 0 equals, let's do the same thing here, but then let's change its color to red just for reference. So this is our reference line. There we go. Because now I can, now I have a record for that. Oh, I didn't want to duplicate Bob. I wanted to duplicate Rod. Excuse me. Evil Bob, what are you doing there? I need evil Rod. All right, there we go. There we go. Comma color equals color dot red. This will be reference line. That is way too long for human readability. There we go. Humans are satisfied. Yay. Yep. There we go. There's a nice little Well, why is that changing now, I wonder? Oh, did I not give it a length? I gave it axis equals bob dot pause. Is there something weird happening to my length there? Let's put the rate really, really small. F5. No? That's weird. Okay, well, I'll have a look at that. I might have... the reason is because I have axis, not axis there. I spelled axis correctly down here, but it was just giving me kind of a default axis out there. Oops. Okay, let's try that now. There we go. That's a bit better. Yeah, because it wasn't straight out. It wasn't exactly pi. It was a little bit less than pi. Okay, cool. So now I've got a little bit of a reference line there, so I can get an idea of where the thing started from. And of course, you can probably imagine if we put this initial theta up past 90 degrees, so let's say just a bit shy of pi. yeah, this thing definitely doesn't look like a sine or cosine, and this period is definitely not pi anymore. It's almost 2 pi at this point, which is kind of cool. All right. Okay, cutting back. Okay, so let's talk about what we're going to do next. The next thing that we want to do is add a driving force and a damping force. So we're going to say minus b times theta, or not b, excuse me, that's what you usually call it, but I'm trying to give things understandable names. Minus damping times theta. So the farther, or theta dot, excuse me. So the faster it's traveling, the more there's going to be a force pushing back on it. And that should be a negative, right? 99% sure that should be a negative because it push it in the opposite direction. But let me check on my reference here just to be sure. Obviously, I don't always know where negatives are going. Yeah, it's positive over here. You move it over to this side, and it's a negative. Just like that'll be a negative. And then we'll say plus driving force. Okay. So we'll calculate the driving force up here, but then we'll just put the number in here. Here we'll have the diffie Q. Right now, damping is 0 and driving force is 0, so that should not have any effect on it. Yeah, that's the same graph we got before. Most notably, the amplitude doesn't change, so we know there's not a damping force coming in. So what we will do next time is we'll start to take a look at the damping effect, and then we'll add in the driving force. And then another thing I'd like to do is there's a neat problem you can do where you don't leave this point fixed, where you have it start to move around. And for that, we'll have to go back to the drawing board, as it were, and actually work in some Lagrangian mechanics, which I don't think I've done any Lagrangians on this channel yet. I love Lagrangian mechanics. It's a lot of fun. I don't get to do it often enough, and so I'm looking forward to that. So thank you so much for watching. I will see you next time. Bye-bye.